In this example, we're going to use Beanie Babies as our subject. And the question that I want to ask is that are dog Beanie Babies cuter than the average Beanie Baby? Now, the way that we're going to do this is we're going to rate Beanie Babies on a scale of 1 to 10 of how cute they are. And we've done this. Suppose that we know that the average Beanie Baby has a cuteness of 5.5 and a standard deviation of 2.5 on a 1 to 10 scale. Now, we could do this by telling people that you have to rate them with a limited number of scores, and the average has to be 5.5. So suppose that that's the case. Now, using this same scale, we could have people rate the cuteness of dogs, and we can tell from a sample if Beanie Baby dogs in general are cuter. Now, we know the population mean is 5.5 and the standard deviation is 2.5. And so we'll take a sample of Beanie Baby dogs and see if there's a big enough difference so we can make a conclusion that in the eyes of the people that grade Beanie Babies, can we conclude that dogs are cuter than the average Beanie Baby? And so here we have the 16 data points, and we can see that there's a range of scores. Looks like 3's the lowest and 10's the highest. And since we know the population mean and standard deviation, we can use the sample data to get an average and then use the standard deviate test or the z-test to see if it's significantly different than the population average. So I'm going to go over to the calculator and I'm going to copy this calculator over to the sheet where I'm doing the calculations. Control copy. I'm going to go back over here. You can, when you do this, you can just download the calculator and rename it, but I wanted to do it this way. Now, let's start off with our hypothesis. Our hypothesis is that dogs are cuter than the average Beanie Baby. And since we're saying that they're cuter, not just their cuteness differs, this is a directional or a one-tailed hypothesis. This will make a difference because it's easier to find evidence for a one-tailed hypothesis than a two-tailed hypothesis. So let's go down to the z-test calculator. So it's got some dummy variables in it. Now we know that the average Beanie Baby has a cuteness of 5.5 and a standard deviation of 2.5, so that's already there. Now let's actually measure let's change this to cuteness. And let's enter the data in that we have. So we've got, I'm just going to copy and paste it, the 7, 6, 4, 10, 9, 7, 5, 6. So control copy. I'll paste it in there. And then I want to do the same thing with that second column of data. Control copy. And I want to make sure that gets joined up in the table automatically. So I'll put it down there. Control V. And it did go into the table. So now, and we've got the population mean and standard deviation. There's 16 in the sample because the calculator calculates the number in the sample right away. And so the average is 6.63. Okay, so that's higher than the population mean. So it looks like the sample's cuter than the population mean. But can we conclude that dogs in general are cuter? Can we make this conclusion for all the rest of the dog Beanie Babies? The Z obtained from our test, the z-test, using this formula is 1.80, and the probability of getting that Z in a one-tailed test is 0.036. So that's less than, now for alpha equals 0.5, equals 0.05, we're in, and which we usually have, that's our comparison level. Since this p-value is less than 0.05, what's significant? So we can conclude that yes, dogs really are cuter than the average Beanie Baby. Now let's report this. What do we need to report? We need to report the population mean and standard deviation and the numbers. The sample average we need to report. our z, and our p-value. All of these we need to report when we write this up. Let's, where should we report this? Let's put this up here in our conclusion. And our conclusion can state that the cuteness of dogs, and so that had a mean of 6.63, m space equals space 6.63, is significantly greater than the cuteness of beanie babies in general, where their cuteness level mean is 5.5 with a standard deviation equal to 2.5. So we can say that the hypothesis that dogs are cuter than the average beanie baby is supported. Now we need to include the z and the p-value and what type of, if it's a one or two-tailed test. So we're going to say now control italics z, turn off the italics, space equals, the z is 1.80, comma, now we need the probability with an italic p. You can control I, space equals, space 0.036, and then we'll clarify that it's one tail. Because now look at this, if we'd had a two-tailed test, the p-value would have been 0.072, and it wouldn't have been significant. But because we made a directional test, the p-value is lower, and we were able to detect that it was significant. So that's why it's always important to make a one-tailed test if you can, because you just have a lot more power to detect differences. But if you want to check to see if it's different in either direction, then you need to do a two-tailed test.